Okay, let's see if we can get this time. This is College Algebra for Teens 3.5 continued. And we need to begin with example number 7, which gives us f of x equals 2x squared plus 3x minus 4 over x squared plus 6x plus 9. And we were being asked to graph these. So since this is a rational function, we need to find any asymptotes. We begin by looking for vertical asymptotes and setting the denominator equal to 0. That anything that blows up the denominator creates a vertical asymptote. This factors to x plus 3 squared, and we square root both sides. And we find out that at x equals -3, we're going to have a vertical asymptote. So let's start the graph over here. 1, 2, 3, 4. Just mark it off on 4 in each direction. Hope that's enough, and we'll fix it if it isn't. Okay? You can use your lovely graph grid that's provided on your handout. X equals -3 is the vertical asymptote, so I draw this line dotted here, and I label it x equals -3. Excellent. Good start. Now we can do the horizontal asymptote. To do that, we simply we look at the degree. The degree of the numerator is 2, the highest power of x. The degree of the denominator is 2, the highest power of x. If you have the same degree, remember we had 3 cases, if it's the same degree, you take the ratio of these leading coefficients. So y here, the asymptote will be at 2 over, that's an invisible 1, 1. When y is equal to 2. So on the graph, we need to put our asymptote at y equals 2. So let's go ahead and graph this across this way. Good. That's y equals 2. Okay, now we need to get the function in here. The next thing we usually check for is x-intercepts. We do that by letting y equal 0. So I take this function, and remember we only have to use the numerator because when we multiply by the common denominator, the 0 wipes out the denominator. So we set 0 equal to the numerator on these. And this is not going to factor. You may use the quadratic formula. When you get down to a square root of 41, you're going to have to find a decimal to represent it in order to get it on your graph. I just took it to polysolve, and when I used polysolve, I got as one of the solutions 0.85. I'm rounding to 2 decimal places for the purpose of graphing. That will be accurate enough. And I got a -2.35. With the other solution, we expected 2 because it was the second degree. That's the x-intercept. Now let's go ahead and get any y-intercepts. Let's put these on the graph. We intercept the x-axis at 0.85 right there, and at -0.235, so about right there. To get the y-intercept, we let x equal 0. And I'm just going to go up here and look at this. If I put a 0 in here, that becomes 0, that becomes 0. I have a -4 over a 9. So at -4 over 9, I intercept the y. So at -4/9, -4/9 is approximately 0.44 repeating. So we go about not quite halfway down there. That's the intercept. Now this is kind of weird, okay? If we're going to get closer to the asymptote, either we're going to have to turn around there and go back down and then bump around and come up, or this is one where it may actually cross the asymptote. But we need to check that on all of them. So the next question is, does it cross the horizontal asymptote? Okay, to check if it crosses the horizontal asymptote, you're asking, does the function up here, I'm recording, Zeke. Does this function ever equal the asymptote? Does it have that y value of the asymptote? Is it ever equal to the horizontal asymptote here of 2? Okay, so I'm going to cross multiply here, and I haven't left myself much room. I'm going to get 2x squared plus 12x plus 18 equals 2x squared plus 3x minus 4. Okay, the 2x squared, I subtract on both sides, they go away. Subtract the 3x from the 12x, and that gives me 9x equals, subtract the 18 from both sides, -22, and we get x at -22/9. So it's going to cross the horizontal asymptote when x is negative 22 ninths. Well, negative 22 ninths is the same as negative 2 and 4 ninths, which is negative 2.44. Okay, so when x is negative 2.44, the graph crosses the asymptote. So it's going to cross the asymptote right there when the x is negative 2.4. So just a little bit to the left of the point that you drew just a second ago. Now we have enough to figure out the behavior. What's going to happen to this is it's going to come down along the asymptote there, dip down somewhere in here, we don't really care how much, cross the asymptote again, and then come right back up over here. So we've got a general sketch of it with the important parts on the graph. Now what happens to the left of this asymptote over here? Let's think about this a second. Either the graph has to go down here, and if it goes down here, there will be an x-intercept. But there is no x-intercept over here because we already found the x-intercepts. So we know the graph can't be down here. We also know it's not going to cross this asymptote because we found the only place that it crossed was right there. So that means that when we sketch this, the other piece of it is going to be up here. Okay, and let me show you my graph that I did on my class notes. I don't know that it's fabulous, but it gives you another figure. If you want to look on page 368, example 7 is very similar, and there's my graph on my own little grid. Okay, let's move on to number 7. Number 8. Keep in mind that you can pause this at any point that you want to. Buzz, you might see what he wants. F of x here is x squared plus x over x minus 1. All right, first of all, this numerator factors to x times x plus 1 over x minus 1, and that might be helpful. Okay, we begin this like we do all by looking for the vertical asymptotes. We do that by setting the denominator equal to 0. And we have a vertical asymptote when x is equal to 1. Okay, where x is equal to 1 is my vertical asymptote. Draw a dotted line for the vertical and the horizontal. All asymptotes are dotted. Now we want a horizontal asymptote. And to get that, we look at the degree of the numerator and the denominator. Here the degree of the numerator is 2, and the degree of the denominator is 1. When the numerator is exactly 1 more than the denominator, we don't actually have a horizontal asymptote. We have what's called an oblique or a slant asymptote. Okay? So with that, we need to figure out, that's a line, right? It's going to be a line that slants somewhere through here. We need to figure out where that line is. Well, it could actually go this way either. Okay? And so we take x minus 1 and we divide it into x squared plus x. We divide this as it's indicated to find that slant asymptote. X goes into x squared x times x is x squared. X times negative 1 is negative x. Subtract this, subtract the negative. Okay, that makes it positive. So I have a 2x remaining. How many x's will divide into 2x? Well, exactly 2 times. 2 times x is 2x. 2 times negative 1 is minus 2. So this is going to subtract that, and subtract a negative makes that positive. So I'll have a remainder of 2. We don't really care about the remainder. This is our oblique asymptote. Y equals this. Okay, that's our answer. Y equals that is the oblique asymptote. So that's a line, right? Y equals x to the first plus 2. Okay, so let's plot the line by doing points. Let x be 0. When x is 0, y is 2. Let x be 1. When x is 1, y is 3. But x can't be 1, right? So we have to put a hole there because we can't actually have a point there because when x is 1, our denominator blows up, right? We can't have that denominator. Okay, keep going. When x is 2, y is 4. And let's see, when x is a negative 2, we have negative 2 plus 2 is 0. We get 0. Okay, so I definitely have enough points now to graph my line in here. And make sure that you don't, oops, we need to make it dotted. Okay. Make this dotted up here a little bit. Okay. Got a nice dotted line here. Okay. So there's my slant asymptote, and now we have to do the graph. I probably shouldn't have put that point. It's a little deceptive. I should have just not made it quite so bold, just drawn the line through it. Okay, next thing we always check for is any x-intercepts. To do the x-intercepts, we let y equal 0. So I go up here and I let y equal 0. And remember that wipes out the denominator. So when does 0 equal the numerator? And the numerator is x times x plus 1. Well, if x equals 0 or x plus 1 equals 0, which means x equals negative 1. So we have intercepts on the x-axis at 0 and at negative 1. So there, the graph will cross at those points. Now what about y-intercepts? To do that, we let x be 0. So I go up to the function and I put a 0 in here. 0 times anything is going to be 0 in the numerator. 0 minus 1 is going to be a negative 1. 0 divided by that is 0. So we have an intercept on the y-axis at y equals 0. We already have that, so that makes us feel better to confirm it, I guess. And then the last thing we have to check for before we put the graph here is, does it cross the horizontal asymptote? In this case, it's the oblique. QUE. Does it cross the oblique asymptote? In other words, does this graph of x times x, oh, let's do it as x squared. Let me fix that. Let's do it as unfactored form. You'll see why in just a second. It's not hiding very well. Does x squared plus x over x minus 1, does this ever cross this line? And remember, this line is where y equals x plus 2. Does it ever equal x plus 2? Does it ever equal that line? Do they cross at any point? Okay, so we multiply, and here we have an x plus 2 times an x minus 1 equaling an x squared plus x. So this is going to FOIL out to give me x squared plus 2x minus x will be plus x minus 2 equals x squared plus x. And notice that when I subtract x squared, those go away. When I subtract x, that goes away. So there's nothing over here, and there's a negative 2. And when we get something that is not right, then we say, no, it does not cross. We don't find a solution. If we find x equals 5, then it crosses at that point, right? Here it doesn't make any sense. It doesn't cross. So that means that our graph is going to go along this asymptote, cross over. I don't know how high it goes up, not too high or it'd hit the asymptote, and then on down this way. And then over here, we have to figure out where to put it. Should we put it down here? Well, if we put it down here, there would be another x-intercept, which we know there is not. So that means we have to graph it up in this section. And we just can sketch it up there, and you can make it more accurate if you want. Right now, we're doing what's called curve sketching rather than accurate graphing, okay? Very good. Actually, they say to graph, but we're not doing it terribly detailed. All right, good. That's number 8. We have one more kind of special case, number 9. And then we're going to do an application. Example number 9. We are being asked to graph the function f of x equals x squared minus x minus 6 over x minus 3. And what you might notice about this is that the numerator will factor quite easily into x minus 3, x plus 2. And then the kind of weird thing that happens here is that we have a factor in the numerator and the denominator that are the same, which means we're not going to have an asymptote down there. We're going to have what's called not a hole, an asymptote, but a hole, right? We're going to have a hole in the graph. We're just going to have to graph here f of x, we'll call this capital F because it's kind of a little different, equals x plus 2. That's what we're going to be graphing. But we have to make a hole when x is equal to, in this case, 3, because 3 would blow up the denominator. Okay, so let's look at the graph of this. Where x equals 3, right? Normally we would say we have a vertical asymptote and we'd set it equal to 0. But where x is equal to 3, we're going to have a hole for the y. We've got to figure out what the y would be there and leave a hole. Okay, so all we have to do here is graph the line y equals x plus 2. We did that line just a second ago, I think. So when x is 0, we get 2. When x is 1, we get 3. When x is 2, we get 4. When x is 3, it's not defined because we can't put 3 in the denominator. But 3 plus 2 is 5, so this is the point 3, 5, and I'm going to put a hole there, okay? And then I would go ahead with 4. 4 plus 2 is 6. All right, this is a 5. 1, 2, 3, 4, 5. And then I'll go ahead, -2, it's going to cross over here, and graph this line. It's the same line we had before, I think. Okay, and so here's a graph of this function. It's a solid line. This is not the asymptote. This is the actual function minus the hole. So the original function looked like this. This is the hole. We cancel it out, so we have to leave a hole there, and we graph what's left, which is a simple linear function. Okay? So don't let those confuse you. There are actually some interesting things that happen when the degree of the numerator is more like x cubed over this, but we won't be going into that in this particular section. I'm not sure if we do it all in the course, but we'll find out. Number 10. This is modeling traffic intensity as a rational function. Vehicles arrive randomly at a parking ramp at the average rate of 3.6 vehicles per minute. So they arrive 3.6 vehicles per minute. Okay? That's an abbreviation for vehicles. How's that? And then it says the parking attendant can admit 4 vehicles per minute. Admit 4 vehicles per minute. Okay, so this is the average rate that they arrive. So sometimes more are going to arrive, like they might have as many as 10 1 minute, right? And it'll back up. The admittance people that let you into the garage can only get processed 4 people per minute. Okay, that's the admitting rate and the arrival rate. Okay, and then they tell the source of this. Lines do form it at various times. Part A. The traffic intensity, X. So X tells us the traffic intensity in the parking lot, right, is defined as the ratio of, a ratio is a fraction, the average arrival rate divided by, or to the average admission rate. Okay, so we only have to make a fraction. So in this particular problem, it says determine the traffic intensity X for this parking ramp. So all we have to do is take the average arrival rate, which was given 3.6 vehicles per minute, and divide by the average admission rate, 4.0 vehicles per minute, and we could reduce this, write it as 0.9. Oops, sorry. 0.9. Okay. Looks kind of weird the way I wrote it. Okay. That's the traffic intensity, part B. Next page. The average number of vehicles waiting in line is this. F of x is equal to x squared over 2 parentheses 1 minus x. Let me double check that I'm seeing that correctly. I have my glasses. Oh yes, I recopied it down here. Good. All right, and it says that x is between greater than or equal to 0 and less than 1. And x is what we found up here, and we came up with an x of 0.9, and that is good because 0.9 is in this interval that this function works for. Good. And it says compute the average number of vehicles waiting in line, and that's what this tells us, the average number waiting in line to enter the ramp. So in our particular function, when the traffic intensity is 0.9, how many vehicles on the average are waiting in line? So we take this and we put a 0.9 in there, square it, 2 parentheses 1 minus 0.9. So we put a 0.9 in, the traffic intensity, to see how many are waiting in line. And you'll come up with a 4.05 vehicles, which I would expect that the book will round to the nearest number of vehicles, 4 vehicles. Because if you say how many vehicles are waiting, you won't usually get an answer 4.05. It would be 4, okay? So that concludes this section, and I hope you get your homework done, and I'll see you soon.